The day of the week in this class, and so we're instituting a thing called Free Hint Friday. Show up on Friday and you might get a hint of what's going to be on in an exam or quiz, and guess what? We always turn the video camera off for free hint suggestions for Friday. So I'm trying to give you a word to the wise. Don't skip out on Friday's lecture. You might miss something important. All right. Now, last time we ended off, we began by asking a question. What is it that makes, quiet, what is it that makes a chemical reaction product favored or spontaneous? And we came to the answer of that question. And because this is so important, I'm putting it all on the board here. For a reaction to be product favored or spontaneous, again at STP, we've got to specify temperature, pressure, etc. We now know that delta G reaction must be negative. Simplest way to think about that, the reaction starts up here in free energy with the reactants, and the products are down here in free energy. So delta G is negative because it starts here, high, and ends here, low. We also know that for a reaction to be product favored, it must not violate the second law of thermodynamics. And the second law of thermodynamics says the entropy of the universe has got to increase if the process is spontaneous. So we know also, the second point up there, that delta S universe must be positive. And this beautiful equation ties the two together. It says delta G reaction in joules is minus T delta S of the universe. So basically delta G reaction and delta S of the universe are very similar parameters. But again, to convert delta S, which is in joules per Kelvin, into an energy, you multiply by the temperature. Now the third thing we knew, and we knew it before we started all this, was that also the equilibrium constant must be greater than 1. Now so we want to complete the circle. We do have a relationship between the equilibrium constant and delta G, but it's delta G naught, that unique. So again, what does that naught mean? Standard state. It means I'm going to run this reaction and all the products are going to be initially 1 molar and all the reactants are going to be initially 1 molar, STP. So it's a very unique experiment. Everything starts at 1 molar. That's what the naught means. But you might ask the question, well, what if that's not possible? Or what if that's inconvenient for me? For example, you may have something that's reacting in solution and it's not soluble up to 1 molar. So you can't get delta G naught. But there's this also beautiful equation. So there is this relationship between K and delta G naught, but that's the free energy change when all the products are initially in their standard state. So you start the experiment, but as I said, but what if they're not? And that leads you to this very nice equation, which says if everything's not in its standard state, well, that can be that can be accounted for by Q. Q, we know, is the actual concentrations that you added to the beaker, right? So if you didn't use the standard state concentrations in your experiment, no problem. Plug those concentrations into Q, and that's going to either increase or decrease from delta G0 to give you the delta G reaction. So now we've closed the loop between these 3 statements that we know about what makes a reaction product favored. Its delta G reaction must be negative. It must make the entropy of the universe increase. And the equilibrium constant has to be greater than 1. And this is a very important equation. When we get to electrochemistry, the next subject, all important equation called the Nernst equation derived from this very simple expression for delta G reaction. So you can plug in any concentrations you want. You can look up delta G0 naught. You can look that up in a table. You look that up in a table. Plug in your experimental concentrations, whatever those might be, and boom, you calculate delta G reaction. And again, you might ask, why do I want to calculate delta G reaction? Well, if the reaction is producing energy that I'm going to use to light lights or drive my car, it would be very important to be able to calculate delta G reaction under the whatever experimental conditions I might have in my car rather than standard state. So three very nice equations that sum all this stuff up. Now, what I want to do now is get to a more molecular level interpretation of entropy. So we talked already about the notion that you can look at a chemical reaction and make a prediction as to whether the entropy change is positive or negative. Here's a reaction we know something about. So we could predict that has a positive entropy change or a negative entropy change. Well, we predict that it has a negative entropy change. Why? Because it takes three molecules and makes two. So that anytime you take many particles and make few, that's a negative entropy change. So you would predict delta S naught for this reaction equal negative. Now, we can make it even more negative by doing this. Yikers. Now I've made it even more negative. More negative. Why? Because I took two gas molecules and three gas molecules and converted them to two other molecules already at negative entropy change. But those molecules are in a liquid solution phase. And remember, gases are entropy winners. A randomly walking gas molecule can very quickly traverse this whole room. But in liquid solution, the water molecules keep bouncing off of each other. And so there's this thing called the mean free path, how far it goes on an average after it gets kicked in the butt by another water molecule, how far on average does it go before it gets slammed by one over here. It's called the mean free path. It's much longer in gases than in liquids. So making a liquid even more of an entropy loser here. So more negative. And you might think, so important concepts about entropy. Liquids, lower entropy than gases. Solids are the entropy losers. Lowest entropy. And so we can look at a chemical reaction and predict whether it has a positive or negative entropy. Here's another one. We can take a protein. So again, what is a protein? In the simplest sense, it's a molecule, but it's a long chain-like molecule of many, many repeat units. all 20-some of the different amino acids. It's a possible repeat unit. Long chain-like molecule. There's an end, so that's what the protein is. There's an enzyme called trypsin. There's a couple of enzymes at the TRY that clips that protein chain at the amide linkage and gives the free amino acids. Massively positive delta S. Massively positive. Why? Because we take one big particle and we clip it up into thousands of free, meaning free to randomly walk. Clip it up into thousands of free to randomly walk amino acids. So you might think about it this way. So that's a massively positive delta S. You took one particle and you made thousands of particles. And so, I was going to say about that. All right, so take one particle, you make many particles, massively positive delta S of reaction. And, here's what I was going to say. So let's say that's a piece of that protein chain. Okay? And let's think about now the entropy of that molecule. Well, that molecule has 3 degrees of freedom. Write this down. It can vibrate. It can rotate. And it can translate. Now, translate simply means move in one direction. So translate, has a different meaning, of course, in linguistics. But here I am here, and in a chemical sense, what I'm doing is translating. I'm moving in one direction along a line. So those are your 3 degrees of freedom. Very important. You will be tested on the degrees of freedom. The molecule can vibrate. All that polymer chain, wiggle, waggle. It can rotate. The whole thing can do this or this. As we already said, it can translate. So it has 3 degrees of freedom. Now, if we clip it up with the enzyme trypsin, there are the pieces. I clipped it. All of those pieces now can have all 3 of those degrees of freedom. They can all vibrate. I'm an amino acid chain and I'm getting beat up by the water molecules and I'm vibrating. I'm an amino acid molecule and I can spin like a top if I want to, or do this, I'm rotating. And I'm an amino acid molecule, I got kicked in the butt by a water molecule, and now I'm translating. But instead of one molecule doing that, thousands and thousands of individual molecules are doing it now throughout the solution. Now, I want to return to the notion that is taking a low probability situation and creating a much higher probability situation. Again, coming back to this notion that an entropy change is all about probability. Here's the way I want you to think about it. I clip these chains and the random walk just starts working on this. And this chain moves over, that piece moves there, and that piece moves over there, and that piece moves there, and that piece goes there, and that piece goes there. All those individual pieces now are being banged upon by randomly walking water molecules. What is the probability that at one instant in time, simultaneously, they all randomly walk right back to those initial positions? And that probability is infinitesimally small. Once you send these amino acids out in the solution to randomly walk, the probability of them all coming back in exactly the right order, in exactly the right place to form that chain again, that probability is infinitesimally small. So again, an entropy change is about setting things free, and that also inherently has a probability argument to it, that once you set things free, the probability they're all going to come back in the same place at the same time in exactly the same way, that probability is really, really low. So again, thinking about things that would cause a positive or a negative entropy change, taking one molecule and cutting it up, it massively increases entropy change. And we can think of that in terms of the 3 degrees of freedom: vibration, rotation, and translation. Now, let's start paring back these 3 degrees of freedom. So, in a gas phase, if I'm a gas phase molecule, I have all 3 of those degrees of freedom. I can vibrate, I can rotate. That's just one of the ways I can rotate. It's one of the ways I can vibrate. Look, I can vibrate like this too. So there are many ways. So vibration could be many different ways. I can vibrate like that. So I can vibrate. I can rotate this way. I had a student one time demonstrate this. He was on a cheerleading team. And in front of the class, he ran and did, flips over his hands, one after the other, to illustrate rotation in that plane. I'm not going to do that for you. It's, liability thing. My agent won't let me. Sorry, union rules. Got to get a stunt double to do that. No, stop. All right, now, so vibrate, rotate, translate. But now let's pare it back. Yes, the gas, all those possible. Let's go to the liquid. Yes, I can still vibrate, but certainly the viscosity of the surrounding medium is thicker than in the gas phase. And that really becomes, as I said, a big deal for translation, because in the gas phase, I get boom, hit by another gas molecule, and I just go trucking along, and it's quite some time before finally somebody bangs me off in this direction. But in the liquid phase, that is not true. I get boom, kicked in the butt, and then boom, I get slammed here, and then boom, I get slammed back there. So I can't translate as far in the liquid phase because of the increased viscosity of the liquid. I keep running into my neighbors. So yes, I can translate, yes, I can rotate, and yes, I can vibrate. But pretty much all of those, especially translation, at a lower level than in the gas phase. So it's a gas phase entropy winner. Liquid, intermediate. Now let's consider the solid. Again, we talked about this, that if I'm an atom in the solid, I might be able to vibrate, but typically I can't rotate, and for sure I can't translate because I'm surrounded by my neighbors. So I go from a situation in the gas phase with 3 degrees of freedom to the solid phase, well, I've only got 1 degree of freedom. I can rotate. And this brings up, again, this issue of temperature. So if I'm an atom in the solid at room temperature, I'm happily vibrating. This is all I can do. The whole lattice can vibrate. This is all the freedom we got. But if I start cooling that down, if I'm approaching absolute zero, the rate and the distance that I vibrate is much lower until at absolute zero, all motion stops. So at absolute zero, there's zero entropy. So again, entropy is motion. Wait a minute, not quite. This leads us to the all-important third law of thermodynamics. You didn't even know there was a third law, did you? I get so excited about these thermodynamic laws that I just can't contain my enthusiasm. Third law of thermodynamics. The entropy. S, let's just put it joules per, the entropy S, we're going to put it in units of joules per mole Kelvin. The entropy S of a pure crystalline solid is zero. Okay, now again. It's zero. I forgot the end of the sentence. At absolute zero, third law of thermodynamics. The entropy S in joules per mole Kelvin of a pure crystalline solid is zero at absolute zero in temperature, or 0 K. Now, I just walked you through that idea that I'm an atom in a molecule in a crystal, and I can vibrate if I'm above absolute zero, but at absolute zero, I'm dead. But get this, even that does not necessarily mean the entropy is zero, because we might say, so that's what this pure, it's got to be a pure crystalline solid. Pure. What does that mean? Well, let's consider ice. H2O, solid. It's a crystal. It's cubic. With the H2O molecules lined up like soldiers. Now, that pure crystalline solid of H2O, where every H2O molecule, here I'm an H2O molecule, my head is the oxygen, my hands are the hydrogens. I was vibrating, but now it's absolute zero. I'm not moving. Now that material constitutes what the third law is talking about, a pure crystalline solid at absolute zero. My entropy is zero. But if before you froze it, you added, let's say, a little bit H2S, such that every once in a while in this thing, there's a defect. That defect being an H2S has replaced an H2O. Okay, are you with me? So I just changed a pure crystalline water ice lattice, and I substituted in a tiny amount of H2S for some of the H2Os. Even at absolute zero, the entropy of that substance is not zero. Even at absolute zero, the entropy of that substance is not zero, because there's an entropy of mixing. I took the water molecules and I mixed them with the H2S molecules. So So even at absolute zero, that crystalline solid does not have zero entropy because there's an entropy of mixing. And it's easy to rationalize the opposite process. Heat the solid up till it melts, let it evaporate, and send everything out to randomly walk. It'd be much harder then to again mix the H2S in. Somehow I've got to collect the H2S and mix it into the crystal. And so third law of thermodynamics is very clear about what has a zero entropy. It's got to be pure and it's got to be crystalline. It can be crystalline, but impure, still has entropy. The entropy of mixing those two substances, the H2O and the H2S. Okay, so we got 3 degrees of freedom for liquids and gases, but we only got 1 typically for solids. Now, yes. Okay. Anything else I want to say about molecular interpretation? Oh, yeah. Another way to think about molecular interpretation of entropy. The bigger a molecule, the higher the entropy. The bigger a molecule, the higher the entropy. So, if a molecule is composed of 2 atoms, it can vibrate like this. But if it's composed of 4, it now has much more opportunity to vibrate. It can vibrate this way. It can vibrate this way. It might wag. So again, the bigger the molecule, the higher the entropy S. And the easiest way to understand that is that notion of vibrations. That the more pieces a molecule has, the more opportunities it has to vibrate. You can think of a long chain-like molecule doing the wave or something. And so, again, going back to the notion, for example, on quiz 3 or exam 3, predict which has the higher entropy. You're given a family of molecules. One determining factor might simply be the size of the molecule. That if the biggest molecule in general will have the highest entropy. So, trying to give you a molecular level interpretation of entropy and using that information to predict whether a reaction has a positive or negative entropy change. All right. Let's see. Yes, okay. Very good. All right, now, so I want to give you a little bit of the math of entropy. And so let's consider let's begin with one of my heroes in science, Ludwig Boltzmann. So Ludwig Boltzmann is one of my heroes in science. Now I won't remember all my heroes. Let me give you my 5. I think I got 5 heroes in science. Who knows? You might get this on the final exam Name the Colonel's 5 heroes. Marie Curie, number 1. Why? She won 2 Nobel Prizes. One in physics, one in chemistry. This at a time when women were anything but encouraged to pursue careers in science. She persevered, she worked hard, she was smart, she was at the right place at the right time. That is so important in science, to be at the right place at the right time and realize you're at the right place at the right time. So for that reason, Marie Curie is number 1. After that, goes to Albert Einstein. We understand the universe to the extent that we understand the universe around us, and that's at this point a highly problematic statement. It's due to Einstein. One of the most beautiful, his general theory of relativity taught us about what the universe is and the fabric of the universe, this thing called space-time, and all these bizarre predictions about, things can't go the speed of light because their mass increases. All this is due to Einstein. It's beautiful, beautiful theory, and it sums up everything in the universe. All right. Then, Boltzmann. And I'm going to talk about him in a minute. Maxwell. That would be James Clerk. And then finally, Michael Faraday. So these are my heroes in science. Faraday, can't spell his name. We'll talk about Michael Faraday when we get to the when we get to the electrochemistry part. But so Ludwig Boltzmann is one of my favorite. So you know Marie Curie, you know Albert Einstein, obviously. Michael Faraday, looks like a child wrote that. Michael Faraday we're going to learn about with the next chapter. James Clerk Maxwell. No James Clerk Maxwell, no Albert Einstein. Einstein freely admits he was building on the mathematics and physics of James Clerk Maxwell, who was a Scottish physicist mid to late 19th century. And we know that the speed of light is... What's the speed of light? 3 times 10 to the 8 3 times 10 to the 8 meters per second, 3 times 10 to the 10 centimeters per second, right? In a vacuum. How do we know that? Good answer. No, in fact, light goes in a straight line. This might be the one exception. James Clerk Maxwell was the first to calculate that in the 19th century. All right, but what about Boltzmann? Ludwig Boltzmann explained entropy to the world. Here you are, freshman chemistry, 100 years later, and you're studying his work. Very, very important work. But he lived in the late 19th century, and the atomistic theory of matter was not yet widely believed to be correct. So that seems crazy, doesn't it? That people would deny, physicists, that matter is composed of atoms and molecules are composed of atoms. But at that time, in the mid to late 19th century, that was not fully understood or appreciated, and there were 2 broad camps. The older camp said, no, it's something else, and the younger physicists said, no, it's all about atoms and molecules, and we're not going to make any progress in physics until we recognize how matter is made up. So as we'll see here, Boltzmann's work is all about entropy changes, setting molecules free, positive entropy change, corralling molecules up, negative entropy change. And so he's trying to publish his work in this leading physics journal published out of Berlin. And the editor of the journal doesn't believe the atomistic theory of matter. And so Boltzmann is trying to publish this work that is so important that we still talk about it today. And the journal editor is a fossil who doesn't understand modern physics and is rejecting his papers. So this caused him great consternation to the point where he ended up taking his own life by shooting himself. And of course, he didn't get to live to see it, but everybody now agrees that his work was right and that the dinosaurs who didn't believe it died off, as dinosaurs do. I ain't no dinosaur. So that's Boltzmann, and you know that I am crazy for the random walk, and you know that I love entropy and entropy changes, so he is like a god to me. Now, on his tombstone, on Boltzmann's tombstone in Vienna, he was an Austrian physicist. It's not exactly this form of the equation, you can look it up, is that equation, where S is the entropy of let's call it entropy, joules per Kelvin per molecule. So it's the entropy that the molecule has. K is the Boltzmann constant in joules per Kelvin per molecule. And W is a probability term. Probabil. You think I've spelled this word before? Probability term. One way to think about it is that it's the ways to arrange the molecule. So you might think about it this way. That here's a flask. And inside this flask is one molecule. We want to cap it so it doesn't get out. Now, one way to think about this ways to arrange the molecule is that at one particular instance in time, that molecule might be there. That's one way to arrange it. But maybe, due to the random walk, I'm going to leave that one. It's not there anymore, but I just want to illustrate the notion that it was there. Now it's there. So we can think about, well, there are two ways to arrange that molecule. It could be there, or it could be there. But wait a minute, it's not that simple. It could go over there. Now we can think there are three ways to arrange that molecule. It could be there, 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 but in fact there are lots of ways. It could be here, 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 anywhere in here. Many, many ways to arrange that molecule. Now, I want to put this, so this is Boltzmann's famous equation, and again, W is a probability term. Let's think about that probability term a little more. My heroes, there they are. it on a per mole basis. Let's put it on a per mole basis. So let's take our S, which is joules per Kelvin per molecule, per single molecule, and let's multiply that times Avogadro's number, which is molecules per mole. So boom. We just went from joules per Kelvin per molecule to joules per Kelvin per mole. We like moles. So we're going to take K, also joules per Kelvin per molecule, and we're going to multiply it times A, molecules per mole. And so now again, I've got joules per Kelvin per mole, and that's natural log of W, the ways at which the molecule can be arranged. So now I took Boltzmann's equation, famous equation. Oh, by the way, K is the Boltzmann constant. But here's the cool thing. K times A has units of joules per mole Kelvin. That's R. So another way to write Boltzmann equation, joules per Kelvin per mole, is R joules Kelvin mole times log W. So now I took Boltzmann's famous equation and I put it on a per mole basis rather than a per molecule basis. And the reason I did that was to pose this question. I got this flask here. I got a mole of gas. And then I got a little valve type thing. And then this is going to be 1 liter. This is also, sorry for the drawing, 1 liter, but initially vacuum. Okay. Now, so initially I got a mole of gas here in that liter. Now let's go back to this notion of the ways that I could arrange those gas molecules. Again, taking any individual molecule. It could be there, but it could be here, but it could be there, but it could be here. Lots of different ways to arrange now that mole of gas molecules in space. And since they're randomly walking, all of those different configurations are being sampled as time progresses. But now what happens when we open the valve? Well, we know what happens. The gas fills the vacuum, and now you got randomly walking gas molecules in both of those flasks. So the ways to arrange the molecules went up dramatically. Because before, yes, this molecule could take any position anywhere over here, but now it can go here and here and here and here and here and here. So all these molecules now are randomly walking through these 2 1-liter flasks. The ways to arrange those molecules has increased dramatically. So we would call that the delta S for that process. Has to be positive. Because again, S is R log W, well, that's the ways to arrange it. Now, here's a very cool, so we can write delta S is R log, call it W2, W1. This is ways to arrange in 2 liter. And this is ways to arrange in the 1 liter case. So that's the delta S for that process. And according to Boltzmann, we ought to, that should have a positive delta S. But here is a really cool and powerful thing. The ways to arrange the molecule simply increases with volume. We just demonstrated that. We proved that. We had all the molecules on one side. We could arrange it in a certain set of ways. Give them twice the volume. The ways they can be arranged goes up. And so what you learn, and this will be the final thing I say today, what you learn is that W1 is proportional to V1, and W2 is proportional to V2. And then here's a very simple and powerful equation that allows you to calculate exactly that entropy change. It is delta S for that process is R log V2 divided by V1. Very simple idea that, according to Boltzmann, the ways to arrange a molecule goes up with the volume of the solution. So we can calculate exactly the entropy change for that process. All right, we'll pick this up again on Wednesday.